Yeah. So, good evening to this session of week 9 Electrical Measurement and Electronic Instruments course. So, we will be discussing about some of the previous questions that can help you in this solving your assignments. And yeah, then we'll be looking at some extra questions. So, so if you have any doubts related to previous assignments, you can ask, uh, and you can ask in between also. So, yeah, I think your exam is also approaching. I don't know when it will be. Maybe mid of October, I guess. I don't know the final date. But yeah, so I think before that, you should clear your doubts, like whatever you have. And I think the last session, last live session will be on 17th of October. So that will be for week 12. So before that, you can like clear your doubts either in discussion forum or in like by attending any of the live sessions. So yeah. So let's start with the yes, some of the assignment questions. So the first question, it says that yeah. It's not that clear, but still I will read that for you. So the first question says that the successive approximation register of a 16-bit ADC is driven by a 1 kilohertz clock. How long does this ADC require to convert an input voltage? So like they are talking about this SAR, successive approximation register, and one thing we'll have to keep in mind that the number of bits the number of bits is equal to the number of clock cycles being taken by SAR to convert that for conversion. So and we know that there's this 1 kilohertz of clocks frequency it is given. So they are asking for to how much time it will take. So time, if we talk, yeah, so if we talk about the time, then it will be this 16-bit is what, like number of bits in SAR is equals to number of clock cycles taken by it. So that means this SAR has taken 16 clock cycles. So we have 16 and we know the frequency of that. So based on that, we can calculate that the time rate, that is TR, which is 1 by 1 kilo, that will be 1 milli. So if we multiply this with one pulse, like time rate with all the total pulses, all the total clock pulses, then we will get the like total time in milliseconds taken by SAR, successive approximation register. So yeah, this is simple. Then we have next question. How many comparators are required for a 12-bit flash ADC? So I think you have read this about in the lecture, and so there is a direct formula for that. So you don't have to like memorize like each and every time how many comparators will be there. So the formula for that, it's number of comparators for flash ADC. I think it's 2 to the power n minus 1. So you know so n is basically the number of bits. Okay, so we know number of bits, so we can calculate this thing easily in this question. So I think this is also fine. Just you have to remember this formula. Then we have common data for the next like four sub questions. So the first question says that consider a linear ramp type. So they're talking about ramp type ADC. So which is having a peak value of 2.5 volts, and the counter has 12 bits and is driven by a 25 kilohertz clock. Estimate the maximum value of input voltage that can be converted. So they are asking how, like, till what value it can convert the volt, like till what value of the voltage it can convert that like properly. So we know in ramp, like the peak value which is given here, it's like till that value only it can convert, it can do conversion. Beyond that, the comparator will not work in that ramp type, so the clock will get switch off. So that's why we will have like maximum value of the voltage will be till the peak value of the ramp. Till then it can do conversion. After that it cannot. So this thing you have to keep in mind. So that's how you solve this question. And then the next question, estimate the resolution of this ADC. So resolution is basically the minimum voltage level it can measure or it can convert. So then it's like we have the peak value or the maximum value of voltage which it can convert, that is like 2.5 volts we have, and we divide it by 2 to the power n. So like you have seen somewhere people use, like instead of 2 to the power n they use 2 to the n minus 1. So this is basically these two, like these are based on the conventions, like one is I think some IEEE convention and another one is some another convention. So but it will not make that much of difference in your final results, but just for the knowledge. So I didn't I'm not able to recall the exact standards for which people use this, and people use this. So I think this is being used for, maybe what I read like earlier, it was for the market products. When then ADC is in a final product phase, then I think we use this one, this formula for calculating the resolution of that. When it is not in like product phase or market phase, or normally when we are using, when we are solving questions, maybe we use this, but that's just an extra knowledge. So anyway, we will go with this formula. So we will have 2.5, 2 to the power, we have 12 bits here, to the power 12. So you can get the resolution for this is also easy. So I think you will get a lot of questions based on the resolution, so you should know, like it's simple, this formula is simple for calculating resolution of the ADC. Okay, then the next question, estimate the maximum time required for conversion. So since so we are talking about ramp. So for ramp, the number of clock cycles it takes is 2 to the power n minus 1. So this is important that you should keep in mind. And if you multiply this with the time period of one clock cycle, then you will get the total conversion time. So this will be the maximum conversion time for this. So then, so this will be this. So we have 2 to the power 12 minus 1, and T clock we know that is 25 kilohertz. So this will be like this. Okay. So, so the answer you can calculate, you like calculation you can do on your own. I think there is some, I'm writing here like, and then there's some lag when it is coming on the screen. Let me check. Wait. Okay, some issue with the net, but okay, fine. We'll see. I think till now it's I think fine. The lag is not that much. So the next question, estimate the ramp rate. So ramp rate, as they said, volts per second. So how like the rate at which it is converting that voltage. So it is basically, since we need that rate, so rate will be with respect to the maximum value of the voltage 2.5 and the corresponding maximum time it took for this, it takes for this conversion of this voltage level, and that is what we calculated from this. So we will use this, and I know the solution. This for this it was 163.84. So this will be 163.84 milli. So you will get the ramp rate in volt per second. Okay. So this is also fine. Then the next question. So the next question is again a question common data for the next three sub questions, and so the question says that consider a dual slope type voltmeter driven by a 10 kilohertz clock. Okay, so they are talking about this dual slope type voltmeter. The voltmeter has an integration time, so they are saying TI, the integration time is 1000 clock cycles. Okay, one information we have. Then the next one is like during a voltage measurement, the de-integration time TD I'm just writing this convention. You can write your own convention. I don't know why this net is so slow. Yeah. So am I audible, or is there a lag in my voice? Somebody can reply in the chat. Yes or no. Yeah. Like, am I audible? I think I am facing some lag here. Anybody can reply in the chat. Yes. Okay, am I audible? Okay. Is there a lag in this, or like it's fine with this? Uh, is there any lag? No. No, sir. Okay. Okay. Thanks. 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 Okay. So yeah. So yeah. Following the question. So de-integration time TD, it's 30 clock cycle. So as you have read, like first it integrates, then it deintegrates. So we have this TD, that is deintegration time, that is TD, and then we have this TI, which is integration time. This one, okay. So this is the case for dual slope type voltmeter. Dual slope type, basically analog to digital converter. And then we have this reference voltage. They have given V reference equals to 2.5 volt. Okay. So then they're asking estimate the value of the input voltage. So I think so if you know, like if you have read about this its formula, and also like it's easy to solve directly. So we have this, like we input into t integration time equals to v reference into t deintegration time. Okay, if you know this formula, then you can solve this. So we input, we don't know. Ti is, since clock time, because this is cycle, the clock, the per cycle time for the clock is same for the integration and the integration period. So then we can just only keep it this cycles here. And then we have this reference voltage, and we have the integration time. So solving this, we will get the input voltage as it will be 75 millivolt. Okay, so this formula is important. We input into Ti equals to Vr into Td. Then following this question, then there's next question: estimate the measurement resolution of this voltmeter. So again, the resolution will be so it's like, so it's the voltage and the time taken by for like reaching to till that voltage. So like so but earlier we used this maximum, where it was this one resolution. So here it was 2.5 volts. That was the maximum voltage which this ADC took, and the time taken for that was 2 to the power n. So that's why we use this. But if you know the voltage and how much time it took for that to reach, in order to reach that voltage level, then we can calculate resolution from there itself. So we know, if you know V input, we know. And then so for V input, so V input was um, so it's like the input voltage what we gave. So it is the time of de-integration period for this ADC to convert that input voltage and to nullify that thing to this point. So basically it is this level of voltage which this ADC took, and the time taken by that was the de-integration time, TD. So this will be 75 millivolts as we calculated, and 30. Or we can also calculate in another way, like the reference voltage V reference divided by Ti. Okay, which is reference was 2.5, Ti was 1000. Okay, because we know from this formula V input by Td equals to Vr by Ti. I just rearrange the terms here. So if this is the resolution, then this is equal to this also. So either if you know Tr and Ti, then you can calculate resolution, or you if you know we input and TD, then also you can calculate the resolution. Okay, so this is also fine. Then the next question, if the 10 kilohertz driving clock slows down by 12% due to aging, then how much error will be introduced in the meter reading? So say they are saying that clock slows down by 12% due to aging factors and all those stuff. Then how much error will be introduced in the meter reading? Is it 10 kilohertz? Okay. So what should be the answer for this? If you observe carefully again this formula. So what I wrote there, so it was Ti, we input into Ti, we are into Td. So basically these are cycles, number of clock cycles. Okay. This is also number of clock cycles. And but this is not the time taken. So time, if we want to calculate the time, then it would be Ti into the T clock. That is clock time for one cycle. This is the total time for integration period, but this is only the cycles. So if in our formula there's only mentioning of the cycles, not the total time, that is TCLK. So based on that, even if the clock gets aged by 12% or 20% or 30%, then it will not affect the overall or the final output of this ADC, because we are not having this TCLK. It is being cancelled at both the sides, at this side and this side. Okay. So that's why, since there's no presence of the clock time period there, we only have the number of cycles, then it will not matter whether the clock is being aged or not. So there will be no error, so it will be zero in this case. Okay. So, so, so yeah, so that was the thing. Yeah. So now the next question. Next question is which is having the fastest conversion speed, and starting from the fastest ADC to the slowest ADC. So obviously we know flash ADC takes only one clock cycle for its conversion. I think yeah, one clock cycle, and then we have, after that we have uh, this one SAR. It takes number of bits. It takes time equal to the number of bits, and then we have this RAM type. It takes a little more than that. So I will make you write down a table. So if you have pen or pencil, then you can write this table. It will be helpful for you to remember the number of clocks taken by each type of ADC and the time taken by them. So you can write anywhere, wherever you want. So this is type of ADC, then number of clocks, then we have time taken by that. So we have first counter type ADC, then we have successive approximation ADC, and then we have flash ADC, then dual slope ADC, and then ramp. Okay, so counter type is having 2 to the power n minus 1. So time taken will be 2 to the power n minus 1 into TCLK, time period of one clock cycle. Then we have SAR. It is having number of clocks n equal to number of bits that we just saw, and then total time will be TCLK. Then we have flash. It will not depend on number of bits. It will take only one clock number. It will take only one clock cycle, and definitely the time will be TCLK. Then we have dual slope. It is the slowest of all, 2 to the power n plus 1, and so the time will be 2 to the power n plus 1 TCLK. Then we have 2 to the power n minus 1 and 2 to the power n minus 1 into TCLK, that is ramp. So this wait. Yeah, so this one is the slowest of all. Okay, and yeah, I wrote slowest here, and still it is being, it's not still. Okay, I'll think I'll just come. I think I'll just check the connection. Wait. I don't know why the connection is slow. Huh. Maybe now it may be better. Okay, we'll see. So yeah, so this is the slowest kind of ADC, and the fastest is this one. Yeah, fastest. And but the important thing to keep in mind, then you will say why we use dual slope. We use dual slope because it is the most accurate of all. Yeah, of all, like the ones which we have mentioned here. There are better than dual slope also, and people have done a lot. But yeah, for time being, this is the best. Okay, kind of accurate. So that's why we use dual slope. So this was the thing, and so you can write this table down. I'll give you 1 or 2 minutes. After this, we'll be solving some of the extra questions. So if you have any doubts regarding previous assignments or something, or you want me to like give some information about some specific topic, some so if you want to ask some specific topic, or you want more clarity on that, or even if you need some extra knowledge about any of the concepts uh, being taught to you in this uh, course, then you can ask me. You can write in the discussion forum. We can do that in the next session, live session. So whichever topic, it can be like any, even if it is designing of IC, like something like that. So I would love to do that. So just let me know if you need something else, some extra things regarding this. So so I think you have written this table. So let's go to the let's go to the questions of this, some extra questions of this week. So there's a first question. I told that in the last session that these are homework, so I think you might have tried that, but still you can have a look on that. And yeah, so just try this question. Yeah. So the question is okay. Question is not mine. So question is, what is E naught? I think. Yeah, we have to find E naught. So it's just recall, like I told, every time I told, like you have to check whether the op amp is in either positive feedback or negative feedback. So first thing is to keep a check on that. Then we will be proceeding further. So in this case, this is a negative feedback op amp. So I think this, then that's the easiest one to do, easiest one to handle. So because we can use the virtual short concept. So we have 1 millivolt here, so that will be reflected here, 1 millivolt. Okay, so now we have 1 millivolt here. Let's say this is E naught, 1 millivolt. So there will be no current in this direction, so current will be here and here. So simply using any of the nodal, so you can, or this is directly like this is a non-inverting op amp. But let's see if this is that or not. So 1 millivolt by 2 kilo plus 1 millivolt minus E naught by 18 kilo. because it's 0. So if you just rearrange them, then it will be this E naught. So this is nothing but the expression for the non-inverting feedback amplifier. Okay, very simple. So yeah, you think I think you remember this thing. So 1 by R1. Oh, was it that one? Hmm. No, I think what was that? The formula for non-inverting, it was this one, na? 1 plus R2 by R1 something. Yeah. But in this case, no, it's not that. Yeah, so here, so yeah, it's not, I think, non-inverting. Sorry for that. So anyway, like, so if you're not sure, you can go anyway with this nodal things and all. So then you can get to the answer easily. So if this is fine, then so you can solve this easily. So this was easy question. Then the next question. So read the question. So determine the output from the following circuit. You can answer in the chat box also. This is easy. And they're saying so there is an input signal V2. Determine the output from the following circuit. So you have to tell, is it 180-degree in phase with input signal, 180-degree out of phase with input signal, same as that of the input signal. Output signal cannot be determined. So what do you think will be the answer for this question? It's easy. Just remember, like, the output equation for any op amp is like the differential gain into the uh, yeah, the open loop gain of that op amp into the differential voltage V plus minus V minus. So this is open loop gain because we don't have any feedback in this op amp. That means like and V plus is what, V1 minus V2 A over. So the polarity of this output voltage will depend on which one of them is higher in magnitude. So so in this case, like V1 was this, V2 was this, but they would have mentioned. Okay, I think, but we should know what is the magnitude of V1 and V2 is, then only we can answer whether it is out of phase or in phase. 180 in phase. Hmm. Let's say this was 0 and this was positive, then definitely this is 0 and this is positive V2. So this whole thing will be negative. So we will have 180-degree out of phase. But if this would have been negative, V2 was negative, then we would have this as the answer. So yeah, so you should know, like, so like it will be mentioned like which voltage is higher or like that, so you can answer accordingly based on that the output of this one. Okay. So yeah, moving to the next question, which is not the ideal characteristics of an op amp. Now I think you are in this position to answer this question. So input resistance is 0. Is it? Output impedance is 0. Bandwidth is infinite. Open loop voltage gain is infinite. So like so if we go to these options, then input resistance, it cannot be 0 because otherwise there will be an issue of loading means like so normally we should have like infinite input impedance. Why? Because if we are using this as an amplifier and if we are connecting this to some external circuit here, then if the input impedance of this will be less, then what will happen, uh, it will, the current, instead of going from the feedback, it will be going into this, and it will, so we needed some I current which is being injected from the external circuit, this one, and we needed that same current at the output, but we will not get that because some of the current will go inside this op amp, and that is what we don't want. So that's why this op amp should have high input impedance. So definitely, so this which is not the ideal. So this is not the ideal characteristics of op amp. Then we have output impedance zero. Yes, we should have output impedance as zero as when we are attaching some load to it. So in that case, like if we will, so it's like we say it's impedance matching kind of concept. So we need that for amplifiers, impedance matching of the outer circuitry with this amplifier output. So for that, if there will be some resistance output impedance of this op amp, then definitely we won't be able to get all the like uh, like the correct output in that case. So this is done for impedance matching in amplifiers. Then bandwidth, like I told you in the data sheet when I was discussing about the data sheets, then what was happening, like so every op amp is having this innate nature of they act as a low pass filter. Why they act as a low pass filter? Because when you will see their open loop characteristics that you must have seen in the data sheet, or like in general also. So it's like this. So this is a dB scale where like there's magnitude, how much it can amplify the input, and this is the frequency of that. So this kind of a Bode plot. So normally you have seen something like this, like at certain frequency it will start decreasing, and the point at which the gain is one, like in so the when the gain is one in not in dB scale, in this decimal scale, then after that particular frequency is called as product gain bandwidth product. So at after that frequency, what will happen if we are increasing the frequency, then the amplifier will not be able to amplify the gain that much. And yeah, so it will be like ceasing to behave as an ideal op amp. It will be behaving as a like an impractical op amp, or we can say. So that's why like ideally what is limiting these characteristics? Earlier we wanted like gain not to reduce as we are increasing frequency. So ideally we wanted this bandwidth to be like this, and all pass filter stuff. So why? Because whatever frequency we use, it will not affect the operation of the op amp, and it will be able to easily amplify whatever frequency we are using for that op amp. But instead of that, the normal practical op amps show an low pass filter behavior. In it, nature of them is low pass filter behavior. So that's why we have limited bandwidth. So what is bandwidth? Bandwidth is this. So the point till the op amp can give a gain of 1 in decimal scales. Okay, that is the bandwidth of that op amp. After that, it will be reducing. The gain will be reducing. So ideally, we needed this infinite. We need it for this all frequencies, but we cannot get that. So this is the ideal characteristics of the op amp. Then open loop voltage gain, it should be infinite. So this is also important. This is important. Why? Because when you read about this virtual short concept, so what happens, like I'll say why it happens, that virtual short, although you have seen this in lectures also, but there's another way to look into that in terms of this open loop voltage gain. So as I told, we notice what that is open loop gain. If we have no feedback for an op amp, let's say op amp was like this, like a comparator, it was acting. Okay, this was v0, this was v1 something v2. So we will have this v2 minus v1. Okay, and this is open loop gain because there is no feedback there. Now what happens, like so if we rearrange this a bit, and we have this expression. So what can you observe? If open loop voltage gain is infinite, if this is infinite, then what will happen, this whole thing can tends to what, zero. If this will be zero, then v2 will become equal to v1. So then we will get this virtual short concept, virtual short behavior of this op amp. Okay, that's why we ideally need an open loop voltage gain to be infinite. One more way to see this is that if you have this, so I think in control systems you have read this, like a closed loop system have a gain of A1 plus A beta. Okay, so beta is basically the feedback factor, A is the open loop gain. So this is OL, this is AOL, and then is this beta. So what happens, like so this if this AOL will not, I will just rearrange this equation for ease of understanding. So I just took common AOL from numerator and denominator. So what happened, we got this expression. So if AOL was not was infinite, if let's say it was infinite, so then this whole term will be what, it will be zero. So then the closed loop gain will only depend on beta factor. And you might be wondering what is beta. So let's say for an inverting amplifier like this, we have some supply here. So this R2 by R1, so the this one, so whatever fraction of voltage we see here, that is the beta factor, that is the feedback factor. So it is in terms of this R2 by this, so it will be R1 divided by R1 plus R2. So this is the beta factor for this one. So basically what I'm trying to say, I'm trying to say if AOL will be infinite, then our closed loop gain, so this is a closed loop system because we have a feedback in this. Okay, so this closed loop system will be only be affected by this beta, and beta is what, it is only being affected by the resistors value. That means we can control the closed loop gain of an op amp by just changing the values of resistors or whatever we have attached at the feedback of this op amp configuration. Okay, but if AOL was not infinite, it was some limited value, then it will interfere in the closed loop gain. So that means although we will be changing these resistance value, but it still will be affected by this AOL if this is not infinite. So that's why also this open loop voltage gain should be infinite. Okay, this is one more thing to keep in mind. So yeah, so this was there. Now we'll move to the next question. So just read the question and just and try to answer this. So I'll read the question for you if it is not visible. So consider the constant current source in the figure below. So they are saying this is a constant current source. So I earlier also I told, like with op amp we can do n number of things, and one of the applications of that is to get to realize a constant current source. So this is what constant current source looks like. So they are saying that beta represents the current gain of the transistor. So they were asking what is I okay, I'll write the question. So they were asking for, yeah. So there were expressions for that. Okay. So you have to find the expression for this IC, this current. What will be the expression for this? It will be in terms of beta, and we reference, and obviously, yeah, and obviously this R. So this much is the, sorry, this will be IE actually, because this is NPN. So this is IE, this is IC, this is IC. Okay. So anyway, you have to find this only IC. This, but this is IC. IE. This is IE. This is IC. And if you don't know, like, this is Zener diode. So what happens, like, it is meant, I think we have learned this in 12th class, that it is meant to maintain a constant voltage across it when it is in this breakdown region, reverse breakdown region. So that means, like, this can be replaced by a voltage source of like this, and it's having a voltage of V reference here. So we have basically V reference at this point. So if we are considering this to be like this, so this part we are considering that to be a ground voltage or ground potential. As so we can say that this ground potential, because then this will be like also at ground potential 0 volt because of virtual short. This will be at 0 volt. Then what we can do, so this is at 0 volt, then so we can get the value of current in this direction, in this path, in this branch. And if you know the current in this branch, then there's no current flowing through this, because there cannot be any current inside the input terminals of this op amp, because they have high input impedance. And we are considering that this op amp is an ideal op amp. So if there's nothing mentioned in the question, then you should automatically think that an op amp is ideal. So there's no current flowing through that. So what will the current through this, that will be IE will be equal to what? V reference by R. Okay. So now we have IE. So what is the expression of IE in terms of the base current and the collector current of the transistor? That is IC plus IB. Okay, I think this also you have read in your analog circuits course. So if this is the thing, then we need IC. So IB will be what? IB will be IC by beta, that we know. And IE is what? V reference by R. So you can get IC from here. It will be beta, beta plus 1, V reference by R equals to IC, the collector current. Okay, so now just to see why this is being told as constant current source, because Zener diode will Zener diode Zener diode will maintain this constant voltage across it. That's we saw that is V reference. And so this is, we can say, almost constant. And this R, we have decided that R, okay, we have set a value for R. So and beta is the internal intrinsic property of this transistor. So this is constant, this is constant. So somehow we are getting a good stable current source from this circuit. Okay, so it is not dependent on this supply voltage VCC and these other R1, R2 and load. Even that is very important, that it is whatever load you are using here, it will not depend on that. So you can connect any load uh, in this circuit, and then also you will get this constant current. So that's why this is called as constant current source using an op amp. Okay, so if this is okay, then we'll move to the next question. So just read this question, take time, and try to solve this. It's easy, but still, I'll just read that question for you. So the following signal Vi, this signal, Vi is this one, full, of peak voltage 8 volts. So this is basically 8 volts, and this is minus 8 volts, is applied to the non-inverting terminal of an ideal op amp. Okay, so this is an ideal op amp. They have said that, mentioned that. So transistor, so they are saying transistor VBE of 0.7 volts. So this transistor is having, like, the base to emitter voltage, this voltage drop is 0.07 volts. Beta they have given to be 100. Then since LED is nothing but a diode, and its reverse bias voltage is 1.5 volts, or forward bias voltage is 1.5 volts, sorry for that. So VCC is 10 volts, and this is minus 10 volts. So we have these values. Then you have to tell for how many number of times the LED will glow. That means you have to tell how many number of times this LED will be in forward bias. Okay, just think how you will approach. So I think you should start with this question by thinking like we need to see whether LED will glow or not and when it will be glowing. So you have to check at what is there any threshold which is being required for this LED to glow. If yes, then you will have to calculate that. So think like that. And then think like, okay, in which configuration this op amp is being given to you in this question. So here, can you see any feedback in this op amp? No, you cannot see any feedback. If there is no feedback in that op amp, then blindly you have to, then blindly that op amp will be working as a comparator. Okay, if there is no feedback. So if you have Vi here, then Vi at this point, then and this is acting as a comparator, this op amp. So you know that so that means that op amp output will be either 10 volts or minus 10 volts. So it will depend on the polarity of or the difference of these two, V plus and V minus input side of this op amp. So for that, what will be the voltage here? So this is basically simple voltage divider circuit with 2 kilo ohm and 8 kilo ohm resistors, and we have 10 volts here. So this is dividing this in a ratio of 10 into 2 by 10. So this is basically 2 volts. Okay, this is fine. So we have 2 volts here. So and you know that Vi is kind of this wavy kind of structure signal. So whenever Vi will be greater than 2 volts, this is 2 volts. Okay, whenever it will be greater than 2 volts, then the output of this op amp. So I will say Vi when greater than 2 volts, that is this 2 volts. Then the output of this op amp will be what? I will say V output is this one. It will be positive 10 volts. Why? Because the non-inverting side of this comparator is higher than the inverting side of this comparator for Vi greater than 2 volts. That means we have this for this condition. So we came till this point. Now after this, once this point is at 10 volts, is maintained at 10 volts, then let's see what will happen further. We know the and like a transistor to work in like this as an amplifier, I'll say. Then or forget about that. We'll think of that later. But let's see. So this is 10 volts here. So we can see we can simply use a KVL in this direction. So this will be 10 minus 15k into IB. So this is base current which is flowing inside the base terminal of this transistor, equals to what? To 0.7 volts, because there will be a voltage drop of how much? 0.7 volt across the base emitter junction of this transistor. So it is 0.7 volts. Simple, nothing complex in that. So now we have this much knowledge. Okay, fine. Then what else we can do? So we can calculate IB as 10 minus 0.7 by 15k. So this is IB. We know IB. What is IB? So IB will be, it will be 9.3 by 15k. I'm not solving fully. Now let's see, come to at this point. So we have IB, we have the value of IB. Now we can calculate IC from that. That is what? Beta IB. IC is what? Beta IB for a transistor in this common this emitter configuration. So we have beta IB. So beta is what? 100 into 9.3 by 15k. So if we solve this, so we have IC here. Now where is IC in this circuit? IC is flowing here. And why IC is important? Why we are going till IC? Because IC will decide whether this LED will glow or not. I will tell you how. So let's see what is the voltage drop at this point. So 10, this is 10 volt minus 100 into IC. This is the IC current which is flowing in from this branch. IC equals to, let's say this is the LED voltage, VLED. Hmm? So 100. So if we use this expression here, then we will get LED voltage and it will be what? It will be 3.8 volts. Okay. So we saw that we had one comparator thing, and it maintained its output at 10 volts because of the polarity of the non-inverting side is higher than the inverting side. We got 10 volts here. Then we saw that what is the base current of this transistor. Then based on that we calculate the collector current of the transistor, and this collector current will decide whether this how much voltage is required to make this LED glow. So we have LED at 3.8 volts now. In But how much voltage we required for this LED to glow, that is like being given in this question. So if we maintain a value of 1.5 volt across this LED, then it will glow. So we are getting 3.8 volts. So this V 3.8 volts is definitely greater than 1.5 volts. That is the forward bias voltage of this LED diode. That means in this configuration we are able to maintain we are able to maintain the glow of the LED when we are maintaining 3.8 volts here. Okay. So if that is the case, that means when it was happening when Vi was greater than 2 volts. So whenever Vi will be greater than 2 volts, the ultimate result for this will be that we will be maintaining 3.8 volts across the LED, and that will be greater than the this forward bias voltage of LED. That means LED will be glowing. So the point till which this waveform is above, I'll say 3.8 volts. So 3.8 volts will be somewhere here. 3 point, sorry, 1.5 volts. Oh, sorry, 1.5 volts. LED voltage is 1.5 volts. So it will be somewhere here 1.5 volts. 1.5 volts. So if the value is greater than that, then definitely the LED will be glowing. So it will be glowing at this point, but then it will deglow here, like it will off here. It will off because it is less than 1.5 volts. Then again it will be glowing here. Then again it will be glowing here. It will be off at this locations. And you may think, okay, there is a dip here, but this dip is not less than 1.5 volts. That's why LED will remain glow, will remain in glowing position in these two waves, in these two peaks. So how many number of time LED will be glowing? It will be glowing for 3 times. Okay. So 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 like definitely you should be clear about the basic equations of transistor. uh, that is the first thing. Second thing, if an op amp is given to you, then what you should look for, you should look for whether that is in whether there is any feedback given. If not given, then that is definitely acting as a comparator. Third thing, if there is a feedback, then you have to see like whether that feedback is either negative or positive feedback. Okay. So if it is negative, then use your virtual short concepts and all those things. If it is positive feedback, then go for Smith trigger concepts. Okay. So that is important. So this was this question. Then yeah, so we will move to the next question. This, so there is a switch in this, and you have to say what will be the ratio of VOB VOB means when this output voltage when the switch is being connected at the B side, and VOA, that is like output voltage when the switch is connected at the A side. So yeah. So in the circuit, V naught equals to VOA for switch SW in position A, V naught equals to V naught B for SW in position B. Assume that the op amp is ideal. The value of VOB by VOA is. Just try this question. I'll give you some minutes, few minutes. This is easy. Like just you have to see which configuration this op amp is in that's and that in that particular switch position, and then you have to say. And I have like every time I have told, if you don't are able to recognize whether that is inverting or non-inverting amplifier in a negative feedback configuration, then go for this nodal analysis and virtual short concept. That will avoid mistakes. So instead of writing down the straight formula of inverting and non-inverting amplifiers, you can go with that basic nodal equations and virtual short concept to avoid mistakes. Okay, so let's see. So we have in this case we have VOA. Let's see, we talk about first VOA. So when the switch is in A position, so what will happen, I'll make the configuration, I'll draw the configuration. So it is like this, VOA 1K 1K, this is 5 volts, and we have this one. Okay, so this one will not be there, so okay, I will not draw also, but I think then it will be at ground, I think. It's like this only, let's say it's like this. We don't know whether, yeah. So and then we have this, we have 1 kilo. So if this is in position A, we have 1 volt here, 1 kilo here, and yeah, this is the configuration. So now so what will be this voltage? So this is a voltage divider, so this voltage will be zero point 0.5 volts. So and we know this is a negative feedback system, so this zero point 0.5 volt will come here. This will be zero point 0.5 volts. Okay, then what will happen, like so this is open circuit, so there will be no current flowing here, so this is not ground because they haven't mentioned B is at ground or not. So this is open circuit, so no current is flowing, so we only have this branch. Okay, so again use your nodal concept. 5 I'll say zero point 0.5 minus 5 by 1k is in one in this direction, one in this direction, current will flow. Obviously it will not flow inside the input terminal of the op amp, plus 0.5 minus V naught A by 1k equals to 0. So using solving this, we will get VOA as minus 4 volts. Okay. Then now see what will happen when the switch is in B position. So it is VOB here. Okay. So VOB, we will have the thing here, V naught 1 kilo 1 kilo. So this is 5 volts, and so again this one will be there. So now this is 1 volt, and this is 1 kilo ohms, and this A branch will be will not be there, so I'm not drawing also that thing. So yeah, this is the configuration. Again simple, what we have to do, so this is 0 volts, because no current will flowing in input of the non-inverting terminal of this op amp. So 0 volts, so no current here. So this is 0 volts, so this will also be 0 volts. So then it's easy. So 0 minus 5 by 1k plus 0 minus 1 by 1k plus 0 minus v naught by 1k equals to 0. So you can get, so this is v naught b. V naught b will be equal to how much? It will be minus 6. Oh, then you can calculate this ratio. Simple. Nothing there in that complicated in this question. So yeah, again, let's see the next question. Again, there is a transistor. So yeah, in the circuit shown below, what is the output voltage of a silicon transistor Q and an ideal op amp are used? And so this is ideal op amp, ideal. So we have to find the output voltage of this. What will be that? So like just to recall, like what happens for an amplifier. Uh, so this table may be useful, not that useful for this course, but in general can be useful for your electronics engineering. So if this that is in this emitter in this configuration, that is emitter common emitter configuration, then this if that is forward, we say forward active. So you can write down also, you can just see saturation. So these are different regions for that. When you see the characteristics of this, so it looks like this, okay, for a transistor. So I'm talking about that regions. So forward active, saturation, then we have cutoff region for for this transistor, then we have reverse active. So when transistor is to be it has to act as an amplifier, then it is driven in forward active region. So this is amplifier zone. When it is to be act as a switch, then it is either driven in saturation or cutoff. So this is switch region. And reverse action, it's not that much used, but this is used for attenuation. So, so normally we use transistors for amplifiers because even in this op amp itself there are a lot of transistors being involved to realize this full op amp. So what they are doing, they're simply doing amplification inside this op amp. So that's how we get this amplification from this op amp. So a lot of transistors are being are doing their work inside the op amp. So that's why they are that. What does that mean? That means they are being driven in this region. So that just to get an idea. So yeah, these are the reasons. So JE, so for that, like the emitter junction and the collector junction, so how they will be acting? So this will be in forward bias, reverse biased. This will be forward biased, reverse biased, reverse biased, reverse biased, and forward biased. So basically this is the important thing which you have to keep in mind. So when the emitter junction with respect to base obviously is in forward bias, or when when the junction and when the collector junction is in reverse bias, that means, so this is collector, this is base, this is emitter, okay. So this was 0 volts. We know the internal input of this is normally 0.7 volts, and the diode is like this inside that. So what happens? So 0 volt is being given to the anode side of this side, okay, and the cathode side is at V out. So if this thing to be like to be if we have to make this to run in an amplifier zone, then what will happen? We have to make this terminal, we have to make the junction run in forward bias. And how it can happen? It can happen if we are making this V out to be driven in negative voltage. So if this was the diode, this one. So if this was negative, this is 0, then definitely this junction, this diode will be on, and we will have a forward bias here, okay. And for collector junction, this is 0 anyway. And we know that so this, if we talk about virtual short concept, then this is also 0. And so this junction can also be seen as like this, a diode like this. So this is B, this is C. So here we have 0, here we have 0, so this will remain in reverse bias. So that means we got an idea, okay, at least we knew that the collector junction of this transistor is at 0 volts, and we have the base voltage of this transistor is also at 0 volt. So that means the junction of that collector junction of that transistor is in reverse bias. That is one thing. Now on next thing, so then you should think, okay, then in which region it might be working. It can either be working in this forward active region, or it might be working in cutoff region. But for cutoff region, you need junction emitter to be in reverse bias. But in this case, um, what will happen? So, see, so let's say, so how we will see whether it is working in cutoff or forward active region. That is now the question for us. We realize that JC is in reverse bias, that we know. So let's say, initially when we did this configuration, initially any configuration, the op amp does not consider its feedback. So let's say there was no feedback, and this was simply acting as a comparator. So what happens? We have 5 volts here, we have 0 volts here. Okay, this is ground, this is 5 volts. Simple, no virtual short. At the moment when we start, we just connected, we made the we just closed the path for this whole circuit. At that moment, initially, momentarily, this op amp act as a comparator. Then what happened? So this is 5 volts, and this is inverting terminal, and this is higher than the non-inverting terminal of this op amp. Then what happens? So the output of this op amp will what it will come into negative saturation, because this side is higher than this side. So that means this will be negative. Now this was this was just at the starting, at the transition period of this circuitry. So once this output became negative, then what happened? This emitter junction became negative. This base was at 0 volt. Then this base emitter junction became what? Forward bias. And then, since although we have connected feedback, then after that, because of this feedback thing, it will start balancing its output. So what will happen? The virtual short concept will come into picture. So this will slowly start becoming 0 volts, and once it becomes 0 volt, then the base collector junction will become, or it will come in reverse bias mode. That means this transistor is acting as an amplifier. So the motive behind all this story is that to make you know the so you should know, like, in which region the transistor is working in that particular circuit. That is the important thing. So if you once you know that, then you can proceed with the further the question for that, for further, like, if there is some complex circuitry involved in transistor, then also you can solve that. But one tip, which I will share. Normally they keep this, they make the circuit so that the transistor is an amplification zone. So that is one tip that is being, like, that you can also see. But it's better to see, okay, in which region this transistor is lying or it's functioning. So in this, it's acting as an amplifier. And so they said, like, what will be the output voltage. So since this was like um, so this was like, now this is acting as an amplifier. So if I make this circuit, so this is V output. So once this feedback came into picture, and after all this operation, so slowly the V out comes down to what? So this was ground, this is ground. Okay, so this was 0 volts, this is 0.7 volts. We know that it is acting as an amplifier, so there is a 0.7 volt of drop here. So what will be V out? Simple, 0 minus 0.7 equals to V out. I'm using KVL in this branch, from starting from this ground to base of this transistor, and then coming to the emitter side of this transistor. So that is this equation, 0 minus 0.7 equals to V out. Okay, so V out is what? It is 0.7 minus 0.7 volt. I hope it is clear to you. This table is important. I don't know whether you will get such questions in this session, in this course, in the exam, in this course, but it is good to, like, because anyway you will be learning about op amps and all in your electronics and all. So there you will encounter these type of questions, or you may get questions like this in your exams. Who knows? Okay, so it's better to have the understanding of all things. So this was there. So if you have any doubts, then just let me know. I will explain this again. You can anyway go through the video lectures again and again. uh, yeah, just let me know. You can interrupt me. Otherwise we will move to the next question. Yeah. So this is next question. Again, I think this is simple. Assuming the op amps are ideal, the voltage gain of the amplifier shown below is. So just I'll give 1 minute, solve, like, then I will give the answer. It's, I think, simple. So let's say this was Vi. Okay. So it's, I think, simple. I'll just solve because there is one nice question after this. So Vi is this. Let's say this is, so this is V naught from this point. Okay, and then we have, so this is again check whether it's negative or positive feedback. So this is a negative feedback system. Yes, we have negative feedback here. And then so we can use that virtual short here in this thing. So this will be what, 0 volts. Okay, so they are asking for the gain. So just go for the input output, the equation for this op amp. So we will get the answers for all these things. So 0 minus Vi divided by R1. One current is going here, another current is going here. That will be 0 minus V naught by R2 equals to what, 0, because no current will flow here. Okay. So what will be Vi and V naught relation? It will be 1 by R1 R2 then V naught minus. So it will be this. So this is the amplification factor of this configuration. That means R3 and yeah, R3 is having no role in this configuration. So like, one interesting thing which we can observe from this kind of circuit is that, so you should also like think like this, like, oh, let's, we are seeing that the gain is only being controlled by R1 and R2. That means the output voltage which is being shown here is what, is only being maintained by R2, R1 and Vi. It is not dependent on R3. So what you can do from this, have you thought of this? What you can do from this? So if this voltage, so what if this was a load resistance RL? Let's say this was RL, a load resistance. L- In another words, you don't know what R3 was. So irrespective of load resistance, you are getting a constant voltage source. So this can act as a constant voltage source for your application. So if you have to maintain a source, a constant voltage source, which is not dependent on the load resistance, then you can realize using this circuit. Getting my point? Because you can change. So this will be the source voltage. So let's say you have a box, you are getting V naught, and inside that box you have this kind of circuit, and whatever load that is R3, which you are connecting at the output. So whatever that load will be, you will get a, your voltage output will be, your source voltage will be remaining same. Okay. So earlier what we saw a constant current source. See, this one was constant current source. We used it, we realized use this using a transistor. Now we saw another thing which is constant voltage source. Constant voltage source. So next time when you will see any DC voltage source or something which you use normally, then you can think, okay, there will inside that circuit, inside that box which you normally use in your laboratories, that some such kind of circuit is there inside that, which is maintaining that output voltage to be such at stability, at such stable point. Okay. But this is just a, like a very, I'll say, a crude example of voltage source. constant voltage. So because there will be a lot of instabilities that we are not going through, but this you can realize. Okay, so interesting observation. The next question, yeah. Now you tell me the answer for this. You can write in the chat box. It's easy, I think, without pen pencil you can say. Anyone can write whatever they seems is the correct answer. Is this question that tough? Hmm. So I have like always I have told like to check whether the this whether the feedback is positive or negative. So if you will be careful, so if you are careful, then this is a positive feedback. That means it will be acting as a, in this case it is kind of a Smith trigger, where the threshold is what the threshold is being decided by this 0 volts, that is the inverting terminal. Threshold is where like you will be changing your output voltage levels. So this is driven decided by this, and you cannot use virtual short here. So simply use this as a comparator, where you can see that this is 1 volt and this is 0 volts. So this is higher than this one. So this will be what plus V saturation, that is plus 15 volts. Okay. So if you will not see this, okay, you will say, okay, this is anyway simple negative feedback system. This is 0 volts, and then you will solve like this, and you will get either of the answers. So this is the this thing you should careful. You should be careful about that. Okay. So now this next question. So this is kind of a designing question. So uh, so as I told, like op-amps itself means operational amplifiers. That means we can do a lot of operations from op-amps. We just saw, we didn't see that. We will see in this, like we can do addition, we can do multiplication, we can do division, like we can do subtraction. All these mathematical operations we can achieve from this op-amp. Okay, that's why we call them as operational amplifiers, and that is one of the examples which we will see here. So what's the question is saying? Question is saying that there is an instrumentation system. In an instrumentation system, there is a need to take the difference between two signals. So they are saying that they have to take the difference of two signals. One is V1 and another one is V2. Okay, one is V1. So you had two signals, V1 and V2. So I will write down that for you. This 2 sine, so V1 is 2 sine 2 pi into 60t plus 0.01 sine 2 pi into 1000t. Okay, this is V1. V2 is what? 2 sine 2 pi into 60t minus 0.01 sine 2 pi into 1000t. So this, we have two signals with us. Okay, and they are saying we need difference of these two signals. We'll see why we need that. It's written in the question. So draw a circuit that finds the required difference using two op amps And mainly, so they are saying, so there is a constraint, like the engineer is only having 100 kilo ohm of resistor with him or her. And since it is desirable to amplify, and they are saying they need the amplification of 1000 hertz component in the process. So they don't need, so first of all, see how many frequency components are there in these signals. One is 1000, another one is what, 60 hertz. Okay, that anyone can easily say. Same for the V2 signal. Now they are saying they only need this 1000 hertz component and they need amplification for that, and the amplification should be around 100. So they are saying the op amps are available, are ideal. Okay, they are ideal, except that their output voltage swing is limited to plus minus 10 volts. That means like their output voltage is being limited to plus minus 10 volt. That's all. So now the interesting thing is to know here is that why they need to get rid of this. So if you will see, not in India but outside in other countries, there is 60 hertz power lines going through that, and because of that there can be this interference which is being, so see, which is being which is being mixed with the signal, the actual signal which we really wanted to measure. So in this case, let's say, so this was the actual signal of 1000 hertz which we wanted. Maybe some biomedical signal, we don't know. That's it's very less. It's very less. Maybe from some sensors it is coming, but because of these power lines or like the supplies which we use, they are having 60 hertz component. That's why this noise component is being attached to this signal which we need to measure. So that's why, but we don't want this. This is noise, okay? And this is the sensor signal which we want. So that's why we will use the some configuration of op amp, and we will try to realize how we can do this, how we can realize uh, this difference of V1 and V2 by avoiding this noise factor in that. How we can do that? So for that, I'll add one page. So we needed difference. So that means we know that op amps can act as in summing amplifiers. That we know. Okay, I will also show you. And so see, we know that we can do inverting or inverting operation on any signal using inverting amplifier. Inverting amplifiers you have read. And and let's say if we use that operation, after this operation, if we add that signal what we have inverted, if we use a summing amplifier after this, so can we achieve difference of these two signals? So in other words, I'm saying, let's say we invert this v1 to minus v1, and then here in this case we are adding v2 and this minus v1. So what ultimately we will get v2 minus v1. Okay, so I think we got the answer how we will be achieving this designing operation from operational amplifiers. So we need inverting operation, that we know. Then we will be taking help of summing amplifier again with the op amp. So inverting configuration, you know how it is, how it looks like. So this is grounded. We let's say V1 was here, and we can only use R. So there is one constraint that we can only use 100 kilo ohm resistors. There can be multiple of that in series, parallel, whatever, but we are using R. Okay. Then this will get this will we will get what from this? So we will get an inverting V1 from this. So this is what inverting amplifier. Now we need the difference of these two signals. So now we will use summing amplification. So summing amplification is nothing but it's something looks like this, minus plus, this is ground. So V2 will come from here, R. This will be V naught. So this is now summing amplifier. Okay. This is summing amplifier. This was inverting amplifier. And what we achieve finally, we achieve the sum of these two from this, and we got V2 minus V1. And that is the difference of these two signals, and that what was being asked in the question. So if we take the difference, we will remove this noise, we will get the sensor signal. So the output will be 2 times 0.01 sine of whatever there was inside that. So this is the thing, but again there is a constraint. What is the constraint? We need a gain of 100. How we can achieve that? We can achieve that by, since this was R, that's why I cancelled that. And we can achieve that by yeah, so if we use 50 times of R, or we use 50 registers in series with this, although there will be a lot of errors in that because each and every register will have some tolerance, but just for the sake of solving this question, if we use 50 times R, that means 50 R registers in series. In that case, this factor will be multiplied by 50, and then we will get an amplification of 100. Okay, amplification of 100, that means 50 into 200 into 0.01. So final the amplitude will be 1 volt. So what we did, we in this question we removed the noise. Second thing what we did, then we took the difference of these our sensor signal. Third thing what we did, we amplified that difference so that we can get an amplification version of our sensor signal, because sensor signal was very less, 0.01 volts. It is very less, 10 millivolt, it's very less. Okay, so we did three things from this designing. So that's, I think you are then I think you will appreciate the the use of these operation amplifiers. We saw the use of current source, we saw the use of voltage source from this op amps. Then we saw what we saw this thing, like we remove the noise, and we at same time we amplified that thing, sensor signals. So yeah, so these are some of the applications of these op amps. Okay, now done with the op amps. We have, I think, done a lot of questions on op amps. Now let's see some of the ADC and DAC questions. So one question is this. So so first, if we say what is there in this question, so it's like so there is this op amp we have then AND gate, then it is being fed to the clock of this 4-bit up counter, and this 4-bit up counter is being feedback to this op amp. Then this 4-bit up counter is being outputted from binary to BCD converter, and then we are finally getting a LED display of 2 digits. Okay, so this is the configuration, and they are asking the magnitude of the error between VDAC and Vin at steady state in volts is. So first read the question fully. Meanwhile, I will add the page. Hmm. So in the following circuit, the comparator output is logic 1. So this is comparator. Okay, and it is logic 1 if V1 is greater than V2. So this is V1, this is V2, and it's logic 0. Obviously it will be logic 0 if V1 is less than V2. Okay, that is simple for a comparator. The digital to analog conversion is done as per the relation. So we have this bits, we are getting this digital, so we have this digital bits here, digital bits, and it is being converted to DAC, digital to analog, by this binary to BCD converter. Okay, this is the DAC here, and this DAC operates on this principle. There is some circuitry inside involved in that binary to BCD converter, and which is having this equation. What is this? This is like simply use the ends in this. So this B0 by 2 plus B1 plus B2 into 2 plus 4 B3. So the binary to BCD output is decided by this equation VDAC. Now they are asking what will be the magnitude of error between VDAC and V in steady state voltage. So what you have to like, how you will be approaching this. So you have to see when this clock will become zero, so that this 4-bit up counter will stop. If this will stop, then it will stop. Obviously, it will stop the conversion, and that will be a steady state value. Okay, that is simple. That is the first point of thinking from where we will start thinking. That, like, the first concept, the first thing in our mind should be that to make this 4-bit counter stop, then only it will be a steady state for this LED display. Okay, and how it will get stopped? It will get stopped if this clock signal becomes zero. Okay, and when this clock signal will become zero, it will become zero when, so this is the clock, we are giving this clock continuously. This comparator output, it will become zero. Only then this clock will become zero. So we have to see when this comparator output will become zero. So we are doing a back engineering. So this is zero. When it will become zero, when? So it is given here also. When V2, that is the inverting side of this, inverting terminal of this op amp. So V2 is greater than V1. Then comparator output will be what? Zero. That means clock will be zero. That means 4-bit counter stops. That means what? We get steady state. And that's what, and in that particular region we will get this, then we can find this VDAC, and then we can compare with V in. So what is V in? V in is this 6.2 volts which is here, that is V1. So now let's see for how 4-bit counter looks like. So let's say this was ABCD. So ABCD is what? The ABCD. So this, let's say this is the MSB, the main bit. So 0000. I'm just writing the truth table. 1111 So you will come to know why I'm writing this, as like, I'll just tell you 0011 and 01010101010101. Now, so this is the 4-bit up counter truth table. Okay, which we can see here it is. So now when, so this is what, this is 0 1 2 3 4 and so on till what, till 15. Okay, this is till 15. This is the value of them, of these bits, when we convert them into decimal scale. Now we saw that once it becomes zero, then all things will, we need that this to be become zero. That's what we saw here. So when it will become zero, V2 is greater than V1. So that means V2 greater than V1. That means V2 should be greater than what, 6.2 volts, because V1, oh sorry, so because V1 is given 6.2 volts. Okay, yeah, so it is, so it should be greater than 6.2 volts. So let's see at what particular point at this 4-bit up counter we will get something. So this is what, so this is basically V2. How this is V2? Because 4-bit up counter, it is being fed here in this box, and then this is converting that back to analog signal, and that it is being fed to here. Okay, so this is basically DAC. So it is converting digital to analog, and this 4-bit up counter is basically yeah, it is simple, it is just counting in number of bits. So this is acting as a DAC, and this is also a DAC. Okay, so V2 is greater than 6.2 volts. At what particular moment we will get V2 at this? So we know VDAC output is being decided by this equation. So it is B naught by 2 plus B1 plus 2B2 plus 4B3. Okay, this is the scene. So let's say go for this. So this is what B3, this is B2, B2, B1, B0. Okay, these are these bits. Let's say what happened if these were like getting up to 15, or these all were 1111 bits. So the DAC output will be 1 by 2 plus 1 plus 2 plus 4, 4, 5, 6, 7, 7.5. Okay, at 7.5 volts, it is higher. So this is V2 V2 voltage basically. So this is higher than 6.2 volts. Okay, but is this the right answer? We'll see. Let's say if we go a little up, this is 14, this is 13, this is 12, and so on. Let's say what happened at 14. That 14 means when the bits are 1110. For that, it will be 1 by, so it will be 0 plus 1 plus 2 plus 4, 4, 5, 6, 7. So it is 7. Okay, that means these are like getting up getting so there is a difference of 0.5 volts at each step. That means that at 13, what we will get 1101, this one 1101. And what will be the DAC output for that? It will be 1 by 2 plus 0 plus 2 plus 4. Okay, 1101, just keep that in mind. So this will be 6.5 volts. So 6.5 volt is also enough to make V2 greater than 6.2 volts. So once this V2 or VDAC output becomes 6.5 volts, that means in that case our clock will become 0 and 4-bit up counter will stop counting up, and that will be the steady state value for the system, and the LED will be displaying that value. So uh, so they so they asked like what will be the error for this, the magnitude error of between VDAC and VIN. So VDAC is what? 6.5 volts. We input what we were trying to measure, it was 6.2 volts. Okay, so what will be the error? It will be how much? 0.3 volts. So this will be the error for this. So now the next question you can answer. So what will the stable reading of the LED display? That will be 13. Okay, that is the decimal equivalent of this DAC from here. Okay, because this is a binary to BCD converter. So yeah, so that will be 13. Now one interesting thing to keep to observe here is that what is that you saw that, so these are being so these are increasing in a step of zero point 0.5 volts, zero point 0.5 volts. Okay, based on this thing. So how you can reduce this error? If somebody will ask how you can reduce this error, you can reduce this error. So right now they told that this is a 4-bit counter. What if this would have been like a 6-bit counter or 12-bit or 8-bit counter, 8-bit counter? Then definitely uh, if we are going with this only, this formula, let's see if something will get improved in 5-bit or not. Let's see. So the operation will be from n equals to 0 to 4 to n minus 1, and it will be till bn. Okay, bn. So this will be what? 0 1, so b naught by 2 plus b 0 1, so b1 plus b2 plus b3 plus b4. Sorry, this will be 2, this will be 4, this will be 8. Will this affect, will this help in reducing this effect? uh, I don't think so, because uh, the step increasing step thing is being decided by this lower bit of this DAC. So it is again like if B naught will be 1, so it is again 0.5 volts. So again, if there is like this is like kind of a whole number, then anyway this will be increasing in 0.5 volts. So we cannot get more resolution by just simply increasing the bits. That is one observation. Okay, we failed in that, but then how else we can improve this? So then it comes to the internal circuitry of this 4-bit up counter. So if we somehow change this equation to 2 to the power n minus 2 bn instead of 2 to the power n minus 1, if this is 2 to the power n minus 2, then what will happen? It will be b0 by 4, b1 by 2 plus b2 plus b3. 2v3. In that case, we have much more resolution for this. That means this is zero point 0.5 and this one is 0.25. So the minimum value which can be measured by this is 0.25 volts. So we have decreased by 0.25 value by doing this n minus 2, by decreasing this power factor of this 2 by minus 1. So we can increase the resolution of this op amp. So this is a nice observation, like by simply increasing the bits we cannot increase the resolution in this case, but we can do by changing the internal circuitry of this thing. Okay, so this was this question. Yeah, so I think so these two are, I think this I will give you for homework. You should think. uh, so this involves like the application of like simple your basic electrics and some op amp concept, and these two concepts, so if you know that, so although this is a DAC converter, but you can solve this, you can get V naught. So this is a question, you have to first find I, then you have to find V naught. Okay, so these two things you have to find in this question. So I'll pause that for you, so while you will be seeing the YouTube video, you can pause and then you can attempt this question, and then next session we will be solving this thing. And this again, so I'm pausing this, so this is also very nice question. So just so there here, like it's like tolerance of DAC. This also I'm giving you as homework. So we have to find the tolerance of the DAC. So this will revise your measurement error concepts. Plus, it will give that you will have to apply your op amp concepts also, obviously. So then this will be a good combination of these two things. Okay. So yes, by that note, we can end this session here. So if you have any doubts, you can ask, or otherwise, I'll end the call. So if no doubts are there, then yeah, I'll end the call. Thank you.